You guys, I think my notation so far is kind of clunky. Do you think I could just do a little bit of work of cleaning it up?
Yeah, sure.
For example, in my picture, instead of just choosing a value of x somewhere in the each of those subintervals, what if I'm more selective? What if I were to choose the right point of each of these subintervals to create those approximating rectangles? Then I think using this right endpoint process, or I might say what right endpoint rule, maybe even my right endpoint or my right Riemann sum. I think another way I can generate the sum of the areas of these rectangles is as follows. Well, maybe not different yet. Let me be a little redundant. I guess backtracking, what I really do have is that the area is approximated by the sum. As I arrange from 1 to n, of my f evaluated my x sub I bars times my delta x sub I is just that with a regular partition, each of these subintervals have the same length, and therefore I just simply have a delta x period. Where, as we indicated before the break, I think delta x is merely the ratio of the difference in A and B to how many subdivisions I have. However, since I'm carefully selecting these x sub I bars as the right endpoint of each of these subintervals, I get to change my notation a little bit. So how about this, in purple? My first tick is at A. I think my next tick is at A, or is it plus something?
Plus x1.
Close. How about plus the horizontal width of each of those subintervals?
Yeah.
And I think my x sub 2 is going to be nothing more than A plus 2 delta x's. I think my x sub 3 is going to be equal to A plus 3 delta x. I think the x sub I is going to be nothing more than A plus I delta x's. And I think the x sub n is going to be nothing more than A plus n times delta x. You guys, you know I come to class. I make silly little goofy arithmetic errors. Do you think I can just take a quick break and check to see if I made a mistake? Because I think this is the same thing as A plus n times delta x, where delta x is...
B minus A, right?
Ah, but shoot, my n's cancel. I'm left with an A plus B minus A, which is nothing more than...
B.
Oh, but it should be. I guess it checks out. However, that means I have the mathematical legal right to come in and using this right endpoint rule, I can just write this Riemann sum. And I'm going to rewrite this as nothing more than the sum. As I play this game, of my FE valued at A plus I times delta x, all times my delta x. This is going to be a very slick way for me to come up with a good approximation for the area, but I maintain that if I take the limit, as n increases without bound, of this right Riemann sum, it's going to give me the exact area underneath the curve. You know, you guys, I'm getting tired of writing this. Can I change my notation a little bit? And change my notation a little bit. Do you mind if I just use whole new symbols? And the symbols I'm going to use are the following. So I have got, yet again, another integral of this purple thing. I'm going to identify my variable of integration as x. It's just that unlike last week, you guys, I'm going to have what I refer to as these bounds of integration, which merely represent the endpoints of the interval I was subdividing in terms of a regular partition. Now, when it comes to the blue numbers, I've got a name for that. I refer to those as my lower and upper bounds of integration. And you guys have talked about this in the past. Don't yell at me. Please? First grade? Yeah, it's called an add-in. If subtraction is a subtract. And if I looked at the square root of 5, I might think of the 5 as my radicand. For that reason, what I see in purple is what I refer to as my integrand. Thank you, so on top of it. I refer, the red piece, the red piece, again, like it did last week, as my integration symbol. Just a bit of vocabulary. this stuff all the time, and sometimes we just abbreviate it with these collection of symbols. And we'll get into more carefully what the symbols really represent, particularly when I dive into the second fundamental theorem of calculus. For now, I want to get some practice. Getting some practice. You guys, I lost count. Where am I in my tables? You guys, I'm making this up out of thin air. How about this function? That's a graph of a parabola. It opens right or left? Yeah, it opens upwards because it equals positive. It's going to be a function. I'm so glad you're on top of things. Ooh, where's the vertex? 0, -3 is a y-intercept. Where's the vertex?
2 positive 3.
Do we care?
I care.
2
B over A?
Guys, you're math D graduates.
It was negative
Did I write
b
one
over
correct?
2a, so that's just
Negative B
gonna
over 2A is.
be 2 or 1. It's 1.
Positive 1's the x coordinate. How do you
Yes.
find the y coordinate?
You plug it into
Plug
the
one into the rest of
equation.
that function's recipe. What if you didn't remember this negative B over 2A business?
Then you can differentiate it and set the
Very nice.
derivative equal to
Differentiate.
0.
Set derivative equal to 0, find a critical number. That way you'll be looking in. Well, that'll give you the x values to look in. What if you didn't know any calculus?
Then just
So-
run around and scream, and
You can take that output and complete the score on x, can't you?
you could graph it
Yes.
and point to the high point.
Point to the high point or low point. What about this? What about just finding the 2x intercepts? Look halfway in between. There's another viable technique for locating the vertex. The heck with it. We know where it is. It's a positive 1 comma something.
What if there is no x-intercept?
What was that?
What if there is no x-intercept in here?
Yeah,
Up a creek without a paddle.
Really?
there could be no x-intercept. The maximum could be below the x-axis.
There's not an x intercept here. But I still think I can find the vertex by, actually, maybe I'm wrong. Maybe there are x intercepts. Quadratic formula. Doesn't that give you negative b plus or minus square root of b squared? Minus 4ac all over 2a. But aren't those two x intercepts located at negative 1/2 plus or minus root 3 over 2?
That's negative.
Yeah, that's imaginary.
Oh, you're right. Okay, I'll put the i's in. I still think I could locate the vertex by finding the average of those two x intercepts. After all, here's the first one. I don't think
Doesn't mean you can't find it.
Here's the first one. Here's the second one. If I had to try to find the average of those two beasts, wouldn't I just add them together and divide by 2? But isn't that just going to give me a negative 1 more? But that is negative b over 2a. Bless you. Is it?
Yeah.
Did I just make a mistake? I think I did. I can't do my arithmetic. Don't these? I really can't. Don't these cancel?
Yes.
But negative 1/2 minus negative 1/2 is negative 1. I came up with negative 1/2 in my head. Sorry. Divide by 2, and I got negative 1/2. So even though those zeros were complex, it doesn't mean I couldn't use that tool to find the x coordinate vertex. Did you see my point? No pun intended. All right, I just wasted our time. We don't need to do this. I think over the interval from 1 to 4, I think my quadratic function, you said has an x-intercept of negative 1, vertex at negative 1, a positive 1. Cheaters. I'll be quiet. Can you factor?
Nope.
Yes, you can.
X minus 3.
Oh, but that means I got an x-intercept at positive 3, 0? And negative 1, 0. I think the parabola looks something like this. You guys, I'm cheating a little bit on the keyboard. Do you notice how I'm not unitizing my vertical axis? But at least I've got the interesting points in terms of x-intercepts sketched in the graph. Now, if I'm going to find the area between this curve and the x-axis from 1 to 4, let's look at the picture.
Wait, isn't there like a technique where you just put 3 on the other side of the equation and then you find what can be multiplied in the negative 2, or what can be added, what number can be added? Yeah, difference in squares, and you just get
understand what you're saying. So you're saying set f of x to be 0, and you're saying send 3 to the other side, and then what was that?
And then like,
Or are you thinking of the complete square method?
complete the square. That's
You know,
what-
I'll do it your way.
Sorry.
That's okay. If I add the square of half the coefficient of x to both sides,
Yeah.
I think that generates for me a trinomial equivalent indeed to a perfect binomial square.
Yeah.
And now if I extract roots from both sides, and now solve for x, ah shoot, look what this gives me. 1 plus 2 is, and then 1 minus 2 is, that's just a different way of getting there.
Okay.
Absolutely, I agree. However, if you consider this function over the interval from 1 to 4, let's approximate. What I'm going to refer to as the net area with the right endpoint rule with 3 subdivisions. So everybody, if I look at the interval from 1 to 4 and I subdivide the interval into 3 subintervals, wouldn't that be locating these ticks at 1, 2, 3, and 4?
Yes.
And pictorially speaking, not that I'm a good drawer, but doesn't that mean I use the right endpoints of each of these subintervals to go to the curve? Or the left endpoint rule is fine. You guys, I want to beat that clock tonight. I know I don't have a lot of subdivisions, but you know what? I think adding the area of these 3 rectangles is going to be a piece of cake. Let's give it a shot. I think the area in part 1 can be approximated by looking at, well, the sum of the areas of the ith rectangles as I range from 1 to 3. But that would merely give me a sub 1 plus a sub 2 plus a sub 3. You guys, I'm tired of looking at my picture. I don't want to look at it anymore. Let me just blindly come with these area values by taking my function f and divide at the right endpoint of each of the subintervals. That'd be 2, 3, and 4. Multiply the heights of these 3 rectangles by the horizontal length of each of the subintervals. And because I'm dealing with the sum, I guess I better, well, I just better add these 3 together. Where I think in this particular example, my delta x is nothing more than my b minus a, all over n. What was n?
3.
But that ends up giving me nothing more than 3 over 3, which is simply positive 1. Of course it is. The horizontal length of each of those subintervals is 1 full unit. And I think my function f evaluated 2 is going to give me, I don't remember, I made this example up out of thin air. Is that a 2 squared?
Yeah, 2.
Minus 2 times 2
2.
minus 3 times 1. Plus my function f evaluated 3, which is 3 squared minus 2 times 3 minus 3 times 1. Plus my function f evaluated 4, which is 4 squared minus, help me, 2 times 4 minus 3. You guys kind of cheat a little bit.
I mean, oh, okay.
Look at that middle rectangle. Doesn't have a height of 0. And by the way, the area of the first rectangle is actually, is that negative 3? Plus the area of the second rectangle, which is 0. Plus the area of the third rectangle, which is, if you guys are double checking my arithmetic, is that a positive 5?
Yes.
And so I think an approximation for the area to meet this curve is positive 2. And look at my picture. I don't know if that does a decent job approximating the area of the curve. What do you think? Sounds kind of crude to me, but yes.
Wouldn't the equal sign be an approximation sign technically? Because it's not.
You know, what a good point. Now, technically speaking, I do think that this beast right here is indeed approximating the area of this curve. However, when you look at a1 plus a plus 2 plus a3, that really is this. When you look at this expression, that really is equal to this. Don't take this the wrong way. By transitivity, I do think in the end what I have is equal to this, oh, there's only approximation for that. It's just that I think for every subsequent line, there really is indeed equality that's holding between those two.
Going back to my question before break,
Yes.
is that an absolute value? Because that's going to meet the curve and.
You know, it's not, and that's why I was hoping you guys would say, you don't like this approximation.
I hate it, actually.
And you guys, I can't really say
Why do you?
I'm not doing anything in my head, but it seems to me, if my picture's somewhat correct, it seems to me there should be more negative area than positive area, doesn't there? If you're looking at just the area between the curve and the x-axis. So I'm kind of thinking that this is a fairly crude approximation, I think. How can I make it a better approximation?
Small rectangles.
Smaller rectangles, or how about saying, over the interval from 1 to 4 are more subdivisions. Do you guys agree? As a matter of fact, if I subdivide the interval from 1 to 4 into 80 subintervals and redid this, do you think I'd get a more accurate value?
Yes.
Yeah, I do too. Do you want to see me do it?
No.
Oh, good. So if I did do it in front of you, I'd probably use some kind of technology, but I can do it.
So why did you start at F2 and not F1?
What a good question. I just think notationally speaking, which you'll see in my second part of this question, I just think my life's a lot easier using the right endpoint rule, using these summation formulas. You'll see that in a brief moment. And so I just said, let's just use the right endpoint rule. So for each of these subintervals, I will choose the right endpoint of the subinterval to go to the curve, to find the height of that approximating rectangle.
It was left endpoint, it would have started at 1.
It would. Don't you dare hesitate to answer this question. Who's arguably the greatest mathematician? Arguably. Yeah, you know, he was the first person who used this notion of subdivision like this. Yeah, he was the first person who claimed came across the notion of this process, as we call integration. Here's what he did. He wanted to do a better job than the ancient Egyptians in terms of coming up with a value for pi, an approximation for pi. So he decided he was going to take a circle. And if he can come up with a circumference, and divide the circumference by whatever the diameter is, he come up with
Bubbles.
right. Hey, those are circles, by the way.
That's true.
Quick sketch one, you'll get a better circle.
That's true. Thanks a lot.
Pi.
Thank you. And so he wanted to come up with a decent approximation of pi. And so here's what he did. He said to compute the circumference is too
Scribe.
difficult.
And polygon.
Thank you. He inscribed a rectangle because he can easily compute the perimeter of the rectangle. I said rectangle, sorry. He inscribed a square because it's easy to compute its perimeter. And he used that for approximation for the circumference of the circle, divided by d, and he came up with a lousy approximation for pi. So then he subdivided this into more sides, and he doubled the number of sides, that regular inscribed n-gon. Now he has a regular n8-gon, and he computed the perimeter of that particular piece. And he got a better approximation of pi. And he repeated over and over and over again. And when he repeated it over and over and over again, he got what he thought was a decent approximation for pi, but in mathematics, who cares? We don't care about approximations unless we know how good they are. And he didn't know. So he gave up. And he then circumscribed a square about the circle, and then doubled the number of its sides, and repeated that process over and over again, and over and over again. And so he got both an upper bound and a lower bound for the circumference of that circle, and got the desired accuracy, well, whatever accuracy he desired, and then he got himself a decent approximation of pi, and he knew how far off it was. He's the first person we know of who applied this iterative process. Ah, shoot. I still don't like my question. How about part 2? You guys ready for the big guns?
Bring it.
Sure.
Hey, this is when your life changes tonight. You've never been able to do this before.
Kodak moment right here.
Absolutely. Are you ready?
Yeah.
I think coming up with the exact area, I'm going to value this definite interval. And to value this definite interval, I'm going to take a peek at the limit, as n plays its game, of the Riemann sum as I range from 1 to n of my f divided a plus I times delta x times delta x. And you guys, I just don't give a darn if you remember this particular equation. Because I think looking at the picture, it'll be an absolute piece of cake to put it all together. Where it is the case that my delta x is equal to my b minus a over n, because I'm considering a regular partition of the interval from a to b. And I think in this particular example, I think it's the case that a is nothing more than plus my I times delta x, where delta x is
B minus A over N.
okay, in my example, what's b minus a?
N minus 1 over N.
4 minus
4
1
minus
over
1
3.
over 3.
So 3 over n. Yes?
Yes.
Oh.
So I think my delta x is just going to be 3 over n. All times, oh shoot, look at that, another delta x, which is 3 over n. You guys help me with arithmetic. 3 over n times 3 over n is,
Don't we actually have a value for n here?
what was that?
Don't we actually have a value for n here?
I hope not, because I'm going to take the limit.
Okay.
As then increase that bound. How about saying it this
okay.
way, Bradley?
Yeah.
I'm subdividing interval from 1 to 4 into n subintervals, but now I'm going to take the limit of that.
Okay, I thought we were going over the 3
Okay, you guys
spaces.
are helping with my arithmetic. 3 over 9, 3 over n times 3 over n is...
9 over n.
Yeah,
Squared?
neither, or nothing, because the 3 over n's on the inside of the parentheses, and that one's on the out. Actually, I think what I have to do is evaluate my function at that relatively nasty looking input. And I think this gives me a limit, as n plays this game, of the sum as I range from 1 on up to n. Now my function f evaluated anything is that thing squared minus 2 times that thing minus 3. So I think f evaluated this particular value of x is going to be that particular value of x squared minus, I forget, is that 2 times? That particular value of x. And then it was minus 3. Oh, but shoot, this is the output of my function f with this input, so now I got to multiply all the garbage by my 3 over n. So you guys, can I just routinely come in here and pull out my math broom, clean this mess up? So inside my brackets, is that a 1 plus 6 over n times I plus 9 over n squared times I squared? Minus 2 minus 6 over n times I, and then a minus 3. And now conveniently combining a few like terms, I think within my limit, actually beyond that, within my sum, I have left over, I'll just grab the I squared term first. Is that a 9 over n squared times I squared? I'll now grab all my I terms. Oh, you guys, shoot. I didn't realize I got so lucky. The tab bit of cancellation. And finally, with my constant term, I have no idea. Is that a negative 4? And if you allow me to remove parentheses by taking my multiplication, distributing it over the subtraction, I think that's simply going to give me my 27 over n cubed times I misspoke. 9 times 3 is 27, n, got it, it's an n cubed, times I squared, sorry, minus my 12 over n. But I think that's going to give me this. The limit, as n increases that bound, of some stuff. And I have to confess, you guys, because of our summation properties from last week, the sum of the difference is going to be the difference of two sums. But you know, technically speaking, my index variable I, so if you don't mind, I'm going to pull a 27 over n cubed outside the sum. And I think I got a 27 over n cubed, I said, 27 over n cubed times the sum as I plays its game of my I squared. I also think I've got my minus 12 over n times the sum as I range from 1 to n of just simply 1. It's just that. That's going to leave me with the following. The limit, as n plays this game, of 27 over n cubed times something. You just take a peek at the something. Shoot. We just proven that it's equivalent to nothing more than n times n plus 1 times 2n plus 1 all over 6. And I think on the other side of subtraction operation, I merely have 12 over n times times 1 times the blood operation at my room. It's just an n. Because the sum of constant like 1 added to itself n times is just going to give me n right back. Oh, but shoot, everybody, in the second term, the second grouping, I get a tad bit of cancellation. I'm merely left with that constant. And I think at a glance, you guys can just sit in your chairs, kick your feet up, and tell me what the limit of this beast is right here. I said you guys can kick your feet
27
up.
over 6.
27 over
6.
27 over. How about 27 times 2 over 6?
Oh, yeah, that. I forgot.
Minus. I 12. Where'd you get this?
Well, the n cubes go away.
What do you mean go away? That sounds like Harry Potter mathematics. What do you mean?
Well, when you multiply it out, you multiply the n cubed in the denominator, and you get the n cubed in the
So
numerator after you FOIL it out.
you're saying if you multiplied all this garbage out, the very leading term upstairs would be a 54 n cubed. Downturn, the leading term is going to be a 6 n cubed. And you simply look at the ratio of leading coefficients when those polynomials have the same degree upstairs and downstairs. Are you guys with me? Yeah, this is called math. 29? Ah, shoot, this isn't math 29. Actually, we can come up with that same value a different way. I said we can come up with that value a different way. You know, us in math 30.
Take the limit.
Well, I'm taking the limit. I can
To
multiply top and
infinity.
bottom by 1 over n cubed to come to the same answer. Or actually, because, gosh, there's wonderful French words floating in our heads, we could also use L'Hopital. Don't say it like that. L'Hopital. Either way. Oh, you guys, I have no idea what the answer is. Is that a 9? Minus 12? I'm getting tired. You guys double check my arithmetic.
A lot of work for -3.
Come on, nobody jumped. There was a lot of work, but now we got the exact error. It is good. We weren't able to do that before. Thank you. You guys, I have to confess, I'm being a little goofy because technically speaking, using this right endpoint rule or the right 3-1 sum, you're only going to be able to evaluate this nicely with this technique if you end up generating sums of these i's and I squares and I cubes or maybe just a constant. And if that's not the case, I'm in a lot of trouble. But at least this is a general theory behind evaluating these definite intervals. Are you with me? So if I give you something nicely quadratic or maybe as high as cubic, then I can use these particular identities over there on the left-hand board, the summation formulas, to come with the exact area of these curves.
We have to memorize those for the test, right?
No, I mean, as of tonight, you know them, so.
Oh, of course.
No, we'll just derive them out of thin air.
What's that?
If we forget them, just derive them out of thin air.
Yeah, like I did it. Well, actually, I didn't derive the third one out of thin air, did I? I stated it and said I could prove using mathematical induction.
I feel like this is a dumb question, but I'm still trying to figure out why it's times 2. If you plug in infinity for n, wouldn't that be, infinity times infinity plus 1 and then 2 times infinity? Like, why is just the 2 plugged out multiplied by
I see your point. It's just because the polynomials upstairs and downstairs have the same degree. I think it's a race. I think since the numerator and denominator increase that bound, I need to find exactly which one's ahead of which. And so if I were to come in, can I erase this? Can I just blow up the small picture right here? If I were merely taking the limit as n increase that bound of 27 times this times this, all over stuff, I think if I were to take the time and multiply this garbage out, I get this.
What? Oh, why? What
I'm
does
too
that mean?
tired. I'm just saying, I got 54 n cubed, the leading term,
It's all garbage.
plus something times n squared, plus something times n, plus question mark, or percent symbol, which is just a number. And I think maybe the easiest way to guide this limit is to dive in and merely multiply top and bottom by 1 over n to the highest power I see downstairs, which is 3. That being the case, I've got the limit as n plays this game of just a constant 54, plus some number question mark over n, plus some number pound symbol over n squared, plus some number percent symbol over n cubed, all over 6. And I confess, as n increase that bound, these three beasts do something very nice. They go to 0. But I think that 54 up front, which is a product of the other coefficients, 2 and 27, has a significant effect on the evaluation of slowness, because it was the coefficient of the highest power term you saw upstairs. And so I do think that 2 becomes rather significant in the Do you guys agree? Again, now that this is the only way you can value this limit, there are other techniques, particularly L'Hopital's. It's because I had to use it 3 times. Anybody else before I get rid of this? So, can we go back a minute? Oh shoot, I can't, I just erased it. I have to confess, in practice, this is really what I use if I'm going to evaluate a definite integral. It's just that I think my definition should change a little bit. If I'm going to give a concrete definition, this was goofing me up. I mixed
Question
my
about
colors.
concrete definition.
Yes.
Is this the kind of work you want to see on the test?
Yes and no.
Explain.
Yes or no?
Yeah.
Yeah. But next week I'm going to give you not a regular exam, a final exam. You should expect me also to ask you to find f prime of x using the definition of my derivative function, which is a limit as h goes to 0 of my darn Newton's quotient. You know, I could ask you that question. By the way, should I answer that question next week?
No.
Absolutely
Yes.
not.
Absolutely, yes. It's an exit exam for a first semester calculus course. I need to make sure you got the definitions. Tomorrow when you come to class, you're going to get all over my case. Tomorrow in class, you're going to get all my case because I'm going to give you a shortcut for all this. Just like this is a shortcut to the definition, I'll give you a shortcut for this process. It's just that expect me in the final exam to ask you to go through that definition to evaluate definite intervals. Wow, fabulous. Because it's an exit exam. No tricks. I guarantee you I'll ask you such a question.
Oh, I believe it.
How could he not?
Okay. You
So,
guys,
can you solve that for us?
solve one.
When you just put f prime of x equals limit of h as it approaches 0 of the difference quotient?
Oh my goodness, isn't that a piece of cake?
It's just tedious.
Yeah, so what, you just run through the limit and then
Yeah, you just take the limit
differentiate,
as
or,
h plays its game of my function f divided x plus h.
Yeah. It's ringing a bell.
I'm so glad something's ringing. And this bell's gonna be ringing really loud this weekend where you review, right?
I'll have to use it.
And that more math data just expand the numerator.
So the challenge is so
and so the answer actually does come out to 4x minus 3?
You don't believe me?
No.
You really don't remember this anymore, Brian? This is good.
Huh?
You don't remember this anymore?
Well, I remember him doing this, but I want to see him do it again.
So you guys, is the French technique okay? Becky, I'm so sorry.
Oh, my question was, if you were to ask us this, how would you word it?
I'd be really careful. I would say, evaluate this definite integral using the limit of a right Riemann and using our summation formulas over there. I try to be really careful with the English so there's no ambiguity. It's a test though. And if I have writing that's just not clear, you know you can come up with an answer. It's a test. Well, I'm testing in the mathematics, not in whether or not I can actually write a question. Oh, shoot. You guys, more French technique. You know what? I can't apply the French technique. I think I missed something.
Minus 5 points.
Oh, the H is canceled. Oh, look at that. Exactly what we got right there. You just didn't believe me. You guys, can I tell you my definition? Sorry, can I raise that?
Yeah.
You know, I know I use this to evaluate this definite integral in black, in red. But technically speaking, I could have said this. I think this could be equal to the limit as the norm of any partition goes to 0. It doesn't have to be a regular partition of the sum. As I arrange from 1 to n, of my f divided x sub I bar times delta x sub I. In other words, I could have defined my definite integral in this fashion. I just don't think it's very easy to use in practice like I did over here in part 2 of the last question. I do kind of like this definition, however, because for me, mathematically speaking, it says a lot. It says, I don't give a darn what kind of partition you have with narrow from A to B. I do not give a darn how you choose those values of x in each of those subintervals. If this limit is always the same thing, I say my function is integrable, and that integral is equal to this limit. Again, I know it's not very good in practice in terms of putting things together like it did with the right-hand formula. But I do think that would be a better definition.
Does that work for the left-hand formula as well?
You know, I can make it work. It's just that typically when I deal with sums, and I start off with a value I don't like, I can easily change it. It's beyond the scope of this course. We don't do that here, but I could easily change where I really start. It's sort of like the homework question I think you or Brad had at the beginning of class. I can make it change in how I choose that very first value to accommodate this.
But for us, it's the right-hand formula.
Yeah, for us it's right-hand formula. I promise I'll get more complex in Math 33, where you and I are putting different series together within one equation where we have to match up those beginning I
You
values.
don't have to.
Yeah, we will. It'll be fun. I'll just wait till we study series going back in Math 31. You guys, I stalled. All right, I got an idea. What example was that, number 2?
2i.
Expect so much.
Bubbles.
You never took high school geometry.
Geometry in junior high.
4 years?
You took 4 years of high school geometry.
Dude, that was like 12 years ago.
Yeah. I forget high school.
It's a depressing time in my life.
Any ideas? I asked, any ideas? I can ask that the third time. No, high school geometry.
It's a linear, linear
triangle.
equation.
A what?
Triangle.
A what?
Triangle.
Square.
X-axis, y-axis, y equals 2x plus 3. You guys, I'm not being careful with my picture. I don't think I have to. I think the numbers and the variables say everything. What is this representing? Sort of the perimeter of the perimeter.
So wouldn't it be y prime equals 2x plus 3?
Quite the contrary.
Huh?
I think if I graph the equation y equals whatever's here in any given position, I get this shape. And to talk about the perimeter, I'm gonna.
We're not looking for the perimeter.
Thank you. It's not perimeter. It's looking for area. And so I'm looking for the area of a trapezoid.
Wouldn't you just put that into a triangle and find an area of the rectangle of the square?
Oh, yes, of course you can. I wasn't even thinking that far. I was being lazy. I was just saying to myself, I got a nifty little formula in my back pocket that allows me to compute the area of any trapezoid. It's just 1/2 times the sum of their bases times the height. Where I think one base is this vertical length right here, but that's my function divided by 1, which you said was 5, plus, thank you, times the height, which is, and I think that merely leaves me with a 24. So I think the area is just 24 square units. Piece of cake?
Yes.
Give us that one.
Are all lines like that easy to calculate? I mean,